Breaking the law? No, not at all. The purpose of this video is not to encourage breaking the law. Quite the contrary, this video aims to stimulate our reasoning in order to apply thermodynamic calculations to our mine ventilation practice, being thus even more rigorous than the actual law. In this way, the results achieved will benefit our people and our operations. Let's get to the point. The Peruvian mining regulation says in its Appendix 38 that if air temperatures on certain mining level range between 24 and 29 degrees Celsius, an air velocity of 30 meters per minute must be applied to that level in order to lower those temperatures below 24 degrees Celsius. Then, the required airflow for this given level would be calculated as follows. We multiply the number of levels with high temperatures, in our case 1, by the average cross-sectional area of that level, which would be 172 square feet if we assume a 4 meter by 4 meter drift, and by the air velocity recommended by the law, 30 meters per minute. After doing this multiplication, an airflow of 17,000 CFM is obtained. But could we apply that to the following case? To begin with, we see that the average temperature of the return air at that level is higher than 29 degrees Celsius, so we could not apply what the Peruvian regulation dictates, since it only regulates up to 29 degrees Celsius. Above this mark, it says nothing. And applying an air velocity of 30 meters per minute to places where temperatures are 30 or 31 degrees Celsius may not be enough. What should we do then? The answer would be a detailed heat analysis. We detect every heat source in the level. In this case, each section of hot water. There are sections composed of channeled water and water running uncontrolled through the whole width of the level. After measuring the data depicted in this graphic and using the formulas that I showed in my previous video, which were extracted from the McPherson's book, we can prepare a table like this. This table shows that the channeled water emits a minimum amount of heat compared to the hot water that flows freely over the full width of the gallery. This table also shows that the air velocity needed to dilute the heat is 47.5 meters per minute and not 30 meters per minute. In other words, we would have fallen short in applying the value stipulated by law. Therefore, it is convenient to carry out a detailed monitoring of the heat sources. Here are two extreme cases. The worst case is represented by the level in which the flow of hot water is not controlled. As we can see in the corresponding analysis table, the air velocity in that level should be 56 meters per minute. Again, applying only 30 meters per minute would have been counterproductive. Heat would not dissipate. The best case is this one in which the water has been channeled. We can see that the air velocity to dilute heat is just 6.3 meters per minute. By channeling the water, the heat exchange area between the water and the air is significantly reduced. I recommend carrying out this type of detailed monitoring because it can be used as a tool to compromise the rest of the mining areas to better manage hot water. This monitoring will show that it will not be necessary to invest in expensive refrigeration plants to reduce working temperatures in the environment until the possibility of channeling hot water has been exhausted. I truly hope you like this video, my friends. I hope to see you soon with another video. Please don't forget to subscribe. Bye-bye.